Khalid Ibrahim, you can call the people, please. Send a message for them to join because I am going to start. Oh, this is this. Very secure. So let's go to page. Where did it say you are recording? Okay. Last time, what we did, the last thing that we did last time was that we talked about the different phases which develop in the using the non-equilibrium cooling rate, and we have also developed the TTT diagram, which is the time temperature transformation diagram. We understood from the kinetics of phase transformations there that we can develop another diagram, which is the TTT diagram, which looks like that for the steel. And of course, this is for a specific concentration of carbon that we are talking about, eutectic basically, which is at, oh sorry, the eutectoid, which is at 0.76% by weight carbon. And we also mentioned how the martensite develops. The last thing we said, the mechanism of that we mentioned that the martensitic structure is different from the pearlitic structure, bayonetic structure, and spheroidite structure as well, and that all those three structures are two phases actually occurring together. The martensite is only a single phase, and the other difference is that the martensitic transformation is a result of a diffusionless transformation of austenite to martensite. So it is diffusionless. This means that it is an athermal process. In the other phases, bayonet, pearlite, spheroidite, it is actually thermal process. It occurs by diffusion. This is what we say. By diffusion, a movement of the atoms there cause the change in the structure, and therefore it needs time. In the martensite, there is no time required. Actually, when you quench, we are nearly saying that we have zero time for that. And we said the transformation, the mechanics and the mechanism of the transformation is that the FCC crystal structures have large amount of carbon content in it. So if you quench it very fast, quench basically from the stable austenite zone there, very fast down below 215 degrees centigrade, what's going to happen there is that the atoms which are in the FCC crystal structure, as the crystal structure inevitably changes from FCC crystal structure in the austenite zone to at room temperature to BCC crystal structure, and this is seen also by the phase diagram. I guess we have it somewhere here as well. We said about that. So if you are having there, it is FCC. When you come down there, it will develop a BCC crystal structure. So this is inevitable. Change in the crystal structure, the FCC to BCC crystal structure, but the solubility of the BCC crystal structure alpha ferrite phase to the carbon is very low, as we saw also in the phase diagram. It is 0.022 compared to the austenite. The austenite is very dense in carbon, and that's why when you cool down very fast, the carbon atoms, instead of, if we are cooling it slowly, it will escape. It will go out slowly. It has time. But if we quench, this means that we are theoretically giving it zero time. We don't allow it. We actually we are actually not allowing the diffusion process to happen. We are not allowing the carbon atoms to escape and go and form something else. We are keeping it in, we are caging it in the BCC crystal structure, and trapping it there by reducing the size of the actually from FCC to BCC crystal structure, and this is where it gets trapped. So, and this trapping of the carbon atoms causes this very high strength in the BCC crystal structure, and actually it's like very stuffed in the carbon content, and therefore it cannot accommodate it all together, especially when the carbon content is high. Then what happens there is a net change in the volume occurs, and it changes from a BCC crystal structure to a BCT crystal structure, basically. So this is what we said last time. And that is the route that we could take into development of the martensitic structure. Something to also mention here, that we can therefore show the development of the different microstructures there. If you are having a heat treatment like this, for example, ending up in the pearlitic zone, then you are having a perlite. But also you can control that if you have a bigger jump in temperature and heat it treat in this way, so you will have another perlite. But of course there is a difference between this perlite and that perlite. This perlite, it develops coarse perlite, as we said, coarse. Spelling. My goodness. So okay, we have coarse perlite there. And the other one is we call it fine perlite, and there will be a difference between their behavior, of course. That gives you fine perlite, that is coarse perlite, and the difference between them is in the behavior, because the fine perlite there has much more second phase boundaries, for example, compared to the coarse perlite. Let us explain this. We'll need it later when we are talking about this. So the coarse perlite, for example, let's say very coarse perlitic structure, we will have like this. This is coarse perlitic structure, all right, and like that, okay. While we have the fine perlite, enough to point out with the arrow instead of writing again. And on the other hand, the fine perlite, you will have so many grains and grain boundaries there developing in the material. But not only that, but these lamellar configuration will be also very fine there, as you can see there. Okay, fine lamellar configuration as well occurring. Okay, I'm drawing it. Okay, right. So why is it that their behavior is different? I'm not going to draw it all. Okay, my goodness. I think I could do it there as well a little. Okay, so what happens there is that this is a very fine perlitic structure. What would be the difference in the behavior there between them is that in the, let's say, what happens when we have very large grain boundary and second phase boundary. Now, this is a colony, and this is a grain boundary, actually, a boundary between this and the other grains, because this is polycrystalline now. But also there is second phase boundary also. This is a second phase boundary, the boundary between the alpha, which you have here in the perlitic structure, and the cementite, which you have here. So that is the cementite, okay? That dark one we are representing by the cementite. So that is also the boundary between them is imperfect also, and it is we refer to it as second phase boundary. Now, what happens actually? What in terms of mechanical properties? Well, if we have coarse or fine, it affects the mechanical properties drastically. Why? Because actually, the grain boundary, we explained this previously, or the second phase boundary, they represent basically resistance to the dislocation movement. when you have a mismatch, atoms are in a certain direction, for example, in a grain, when the atoms are in a certain direction, oriented in a certain direction, then any resistance to the movement of the dislocation causes increase in strength. So if the dislocation is supposed to move in this direction, and once they meet another grain, and in the other grain you have the arrangement of the atoms, or the orientations of the atoms are different, this means that the dislocation movement, the dislocation needs to change its direction basically. So what does the grain boundary represent? It represents resistance to dislocation movement, and it's an obstacle for the dislocation to continue moving. Now, if the dislocation wants to move from here to there, okay, how many resistances are there? 1, 2, 3, 4. For example, for that whole range there. While going from here to there, imagine how many resistances it has to go through. A lot of much more resistances, because this is a fine microstructure. So the grain boundary and the secondary grain boundary areas are much greater here, causing more resistance to dislocation movement. More resistance to dislocation movement, which means more resistance to slip. More resistance to slip means more resistance to plastic deformation. More resistance to plastic deformation means that you have higher strength, basically. The higher the strength, as a rule of thumb, obviously gives you lower ductility. And it changes the toughness of the material, because basically toughness is a combination between strength and ductility as well. This also changes the hardness of the material. So the microstructure of the material being fine or coarse obviously affects the mechanical strength of the material. This is for the paralytic structure. This also the coarse microstructure and fine microstructure. This we refer to as the upper perlite also, and this is called the lower perlite. Upper perlite, which is produced at the top, at the upper level of the TTT diagram, and the lower perlite is produced at the the lower levels of the TTT diagram for the paralytic structure. For the bayanite also, we have the same thing actually. When we quench from there, for example, you could heat a treat in this way and get, for example, an upper bayanite, and this is called lower bayanite. And in the same case, in the upper one, and for the same reasons actually, for the upper transformation, for the upper perlite transformation, we will have coarse bayanite. Of course, bayanite generally is much finer than the perlite, but we can distinguish between also upper coarse bayanite with lower coarse bayanite. We can control the bayanite also having coarse and fine microstructures as well in doing this. And why the microstructure fine and coarse are going to be different mechanical properties, for the same reason that we have explained for the paralytic structure which we have here. Now we want to practice, since we have taken the TTT diagram. Guys, are you with me?
وياك دكتور.
Yes, أنا بس أتأكد إن we are connected. Now that we have covered the TTT diagram, we know what it is. We know the creature. This is the animal in front of us. We want to practice using the TTT diagram that if we are given, let me change that to the bigger cursor. If we are given a heat treatment, for example, a history of heat treatment, can we know or predict what the microstructure will be? Well, this is what we want to do, and this is why we have the TTT diagram. We can do that, and we are going to practice that. But also this helps in another thing, like if we know the heat treatment history, knowing the heat treatment history guides us using the TTT diagram to know or predict the microstructure. This also means that we can design any heat treatment to give a profound microstructure, required microstructure for specific mechanical properties as well. So we can design our microstructure also using the TTT diagram. So to start with, we have the heat treatment, and we want to see what microstructure will develop. So we have normally, and we are practicing like if we have a rapid cool to a certain temperature, like quenching, we are doing quenching here, then holding for a time, holding for the time, and as we said, isothermal diagrams refer normally to when you change the temperature, then you keep it at that temperature, you don't continuously change. That is called the CCT diagram, the continuous cooling temperature diagram. Though that's different, that we are not covering here. We are dealing with isothermal. So that's why we normally keep it, hold it at a certain temperature for a while, and then rapidly cooling, and then holding, and then rapidly cooling. It depends on what problem we are having. Now, in the first one, we rapidly cool from the austenite zone to 350 degrees centigrade. If we rapidly cool, of course, this is the TTT diagram. We are assuming that we are in the austenite stable zone above 227 degrees centigrade. Let me just remind you of the, should have brought this here. Let me remind you of that temperature. Where is it coming? To 727 degrees centigrade is the eutectoid isotherm. That is the one. And specifically in this TTT diagram, we are talking about that composition only. So above 727 degrees centigrade, we are in the austenite, the stable zone. The austenite is stable here. Below that temperature, 727 degrees centigrade, at that composition, austenite is not stable here. You see, you don't have austenite. Alpha, ferrite, and the cementite. Austenite will not be stable here, and it is going to transform to the alpha and the ferrite. So in here, at temperatures below 727, it will not be stable. So going back now, if we quench, if we are at the austenite zone, at austenite stable zone, let's say we are at 800 degrees centigrade, and we quench directly to 350. That is 200, and that is 300. This is 400 to 350. That is 350. So we quench to 350 degrees centigrade. If we quench, what do we get by quenching? Yalla shabab. Quenching. By quenching which microstate? Yes?
Perlite.
By quenching, we get perlite. Haram alaikum. By slowly heat treating, we will get the perlite zone here. We already said that, and we can get final. But by quenching,
Martensite.
Again, أحسنت. شنو قلت؟ Martensite. By quenching, we get martensite. But a mistake that the students fallen is that quenching has to be lower than 215 degrees centigrade for the martensite to develop. So if you quench to 350 degrees centigrade, you are not going to form the martensite. No. So while quenching, this is the trick I've used in this question now. When you quench to 350 degrees centigrade, you are falling again in the austenite zone. This is still austenite zone, but this is unstable austenite because we are below 727. The austenite is going to transform, and it is unstable here, but it takes some time in order for the transformation to happen. You have 100% stable austenite here. You quench to 350, you still have 100% austenite, but it is not stable at this temperature. So what is going to happen? The time is going to start from 0 for it. The time will start from 0, and it is going to take that time until it takes. So we are keeping it, actually holding the temperature to 1 times 10 to the 4. So this means we are going up to where? That is 1 times 10 to the 3. And that is 1 times 10 to the 4. So that's the temperature we are at. So up to there, we are up to that temperature. We can draw a vertical line like that. You see? So it's going to be kept like that. Once it reaches to this time here, the nucleation is going to start. This is the nucleation here at this point. And then it is going to grow bigger and bigger and bigger. 50% transformation has completed when it reached there, and then 100% transformation has occurred when you reach that temperature. Of course, transformation to what? To the bayanite phase. So all that unstable austenite is changing into the bayanite phase, and then if you leave it for some time to reach to 1 times 10 to the 4, everything has transformed to the bayanite phase. So that is, if you keep it for that much time, the transformation will be complete to 100% bayanite. Then if you rapidly cool to room temperature, again you are doing quenching here. Now you are going to quench from 350 degrees centigrade to room temperature, which is much below 215 degrees centigrade. So by that quenching, what will you produce? Al-Hin. What will you produce? Shabab, I need an answer. What will you produce? Ivin, huh? Ahad? Anybody? Yes, again, please tell me.
Martensite.
Martensite, صح? So you will be quenching to martensite. This is what you were saying, صح? Again, that is not correct. Again, that is not correct. Why not correct? Because this phase is already formed. The bayanite phase is already formed, the solid phase. That's number one. And quenching from the bayanite to room temperature does not change the bayanite. It still stays as 100% bayanite. The formation of the martensite only occurs by, we explained the mechanism of the transformation there into the martensitic or the martensitic transformation. We said you quench from the austenite, you quench the austenite, which has FCC crystal structure, to below 215 degrees centigrade, which causes the trapping of the carbon atoms in it. This is not quenching from the austenite zone. We are quenching from the bayanite. This will not lead to any martensitic transformation. Martensitic transformation only occurs when you quench from the austenite zone and change from austenite to room temperature, to يعني below 215 degrees centigrade, which causes the transformation to BCC crystal structure, causing the carbon atoms to get trapped in the BCC carbon atoms. This is the only time the martensitic transformation occurs. So you just don't see any quenching and then say you have transformation to the martensite. No, you see, the quenching has to be, first of all, two conditions. Has to be below 215 degrees centigrade. Number two, you need to quench the austenite zone, not any other, or not the perlite, not the bayanite, not the spheroidite, the austenite zone only. When it is quenched to below 215 degrees centigrade, the martensite is going to form. So therefore, this leads to 100% bayonetic structure. Even if you leave it, not quench it, if you leave it to cool slowly, also it develops the same thing. Hopefully now it is becoming clear, the use of the TTT diagram. Let's go to the next one, to the next example. Yes.
يعني الحين حتى البيرلايت لو سوينا لها كوينشن بالتمبرلايت.
Temperlite. Either 100% transformed to perlite and you quench it, it will stay as perlite. It's not going to change. The only transformation, martensitic transformation, occurs from the austenite zone. And the other condition is that you need to quench below 215 degrees centigrade for the formation of the martensitic structure. Above that, no transformation will occur. This is the start of the transformation of the martensite there. Okay? And this is more, and that is more, as we have seen. This is 50%, that is 90%. And above that, no transformation. Below that, then it is going to start happening. Okay?
Okay.
So let's go to the second example. This is the third example. Okay? So in this time, we have rapidly cooling to 250 degrees centigrade, holding for 100 seconds, and then rapidly cooling to room temperature again. So let us see. When we rapidly cool, let's say from again 800 degrees centigrade, stable austenite, to 250, that is 300, this is 200, so in between we have 250. So we quenched there. Again, what transformation occurred? Nothing. Still, this is austenite. This will be also 100% austenite. It did not transform to martensite. Why? Because we are above 215 degrees centigrade there. The minimum temperature for the transformation to the martensite to happen. All right. So this is the minimum temperature there. So we are above that 250. So this means transformation would not occur. But the austenite here is unstable. How much we are keeping it? 100 minutes. So 100 minutes, this is logarithmic. So this is 10, this is 100, this is 1000. So the 100 comes there. All right. So that's 100. This means that we can draw a line there and see up to where we are coming. So if you leave that for 100 minutes, this means that you go with 0 time and start again. 100, 100, it's going to reach there. Did anything change in the microstructure when we reach to 100 minutes, 100 seconds? No change. Why no change? Because we are still in this zone. We are still in this unstable austenite. Still, it needs more time in order for the transformation to occur. So here we are having 100% unstable austenite. Here still we are having 100% unstable austenite. No transformation has occurred. In order for transformation to occur, you need to reach that line, but you are not giving it time enough. You are giving it only 100 seconds. Now, if from here now, if you quench, as we are saying, to room temperature, from here you quench to room temperature, which is below 215 degrees centigrade, what is going to happen? Now, since we have the austenite, we quench to below 215 degrees centigrade. Actually, we are quenching to room temperature. We are forming the martensite phase. But of course, in the formation of martensite phase, you have traces of austenite also developing. Very small amount, 1 or 0.5% or 1.5%. So this is the transformation to the martensitic structure by quenching the austenite there. Quenching from there or quenching from this area at below 215 degrees centigrade causes the development of the martensite also.
دكتور
Yes.
ليش مكتوب 100% martensite في الريزولت؟
وين مكتوب؟
تحت صوب رقم الصفحة.
I am telling you, there will still occur that we have very small amount. يعني this is nearly 100% martensite, صح? But the traces of austenite in research is found that you have 0.5 كمية صغيرة من untransformed austenite trapped between the hard martensitic structure also. But in the يعني just if you want 100% martensite, you go with high carbon content, and we quench to room temperature normally very fast. We get nearly 100% martensite. Okay, but there will be traces always of retained austenite there as well. Retained, yani kept austenite there as well, which get trapped and they don't transform. Okay. Then the last example is basically quenching to 650, then keeping it for 20 seconds, then quenching again back to 400 degrees centigrade, and then keeping it or holding it for 1000 seconds, then quenching to room temperature. This is going to different cycles there. So quenching to 650, that is 650. So when you quench from here to there, well, stable austenite goes to unstable austenite at this temperature. Then if you go to, if you keep it like that for 20 seconds, this is what we are saying, and 20, because that's 10, and this is 100, that is basically 20 from here. So if you extend a vertical line, it will come up to that point there. So this means that you keep it for 20 seconds. This means that we are reaching to this point. And at this point, basically this 100 unstable austenite is going to transform to what? To 50% perlite, because this is the start of the transformation. This is 50% transformation completion. So the austenite, 50% of it gets transformed to the perlite phase because we are in the perlite zone. And again, you have 50% still not transformed of unstable austenite there. So the microstructure will be 50% perlite and 50% unstable austenite. Now, if you quench from there to 400 degrees centigrade, so we quench from there to 400 degrees centigrade. Once you do the quenching, quenching means freezing. You have the same microstructure there, same constituents will be here as well. And then once you are at 400 degrees centigrade, again, no martensite is going to form because we are much above 215 degrees centigrade. Okay, we are at 400 degrees centigrade. So what's going to happen? We go to 0 time and it's going to take its time for the transformation. This is the start of the transformation occurrence at that point. And then if we are keeping it for how much time? For 1000, this means that we are coming up to that point. So we can draw a vertical line there and we say, okay, 50% transformation occurred. We are saying that here we are having the same 50% perlite, 50% austenite. Now what is going to transform? Perlite is not going to transform because it is stable. The unstable austenite is going to transform. Now this is the start of transformation. Transformation of what? Of the unstable austenite. 50%, as you keep it like that, at this point, 50% transformation of austenite has finished. If you keep it more, up to 1000 seconds there, all the unstable austenite is going to change into the bayanite. So the perlite is kept constant, as we could see there. The unstable austenite changed to the bayonetic phase, which we have here. All right. Now, if we are here and if we quench from there, from this temperature, as we see, to room temperature, then what happens? We quench the room temperature. Again, we will be having that same phase there as well. Why? No transformation to martensite is going to happen because everything has transformed into perlite and the bayanite. So the result will be 50% perlite and 50% bayanite there. Any question? No question. All right. Now, yes.
سؤال 50% austenite و 50% bayanite. سوينا لهم quenching below the 215. يصير في martensite ويا perlite بعض ولا ما يصير؟
ما يصير. The only time قلنا the conditions for the martensitic transformation, you need to quench below 215. صح? This is below 215. صح? This is true. But the other condition is that you have to quench what? You have to quench the austenite. سواء كان هني أو كان هني, stable or unstable. You need to quench the austenite. We explained how the martensite develops. It develops by trapping the carbon atoms in the BCC crystal structure while going from the FCC to the BCC crystal structure. So this only happens with quenching the austenite phase only. Moving quenching the other phases like the perlite or the bayanite. No, if you quench perlite or if you quench bayanite, you just freeze them. يعني ما تغيرهم. Okay, we call it freezing. All right.
دكتور أنا قصدي لو في 15% austenite و 15% perlite سوينا لهم quenching below 215. 200.
If you now, I will answer that the question in another way. If we were here, suppose we are here, okay, we quenched from here to this 400 degrees centigrade, and we gave it only time up to that time, whatever this time is, 50% transformation only, okay. So when you reach there, you change from 50% perlite, 50% austenite into what? Now 50% of the 50% austenite is going to change to the bayanite. So in this point, at this point here, you have 50% perlite plus you have a transformed into bainite. How much? 50% of the 50%, which is 25% bainite. It transformed already because we are here at 50 in the middle. So, and you have also 25% austenite. Okay, so we are at this point. What are the phases that we are, the microstructures we are having? You quench from 400 and give it enough time up to reaching to that point. Now we have at that point we have 50% perlite, 25% bainite, and 25% unstable austenite, which we are having here. Now, if you quench from here to room temperature, let's say, you quench from here to room temperature, what is going to happen? The 50% perlite and 25% bainite, they are not going to change. The austenite is going to transform into the martensite phase. So you will have that transformed into the martensite. So you will have the resulting microstructure. The resulting microstructure here will be 50% perlite, 25% bainite, and 25% martensite. Clear?
Clear, Doctor.
Okay. Now that we have learned how the microstructure there, in order to design different microstructures for our purpose of controlling mechanical properties, we need to look at the mechanical properties or mechanical behavior of iron carbon alloys. The different phases of the steel, how do they behave? So this is what I'm saying. We have discussed the effect of processing or heat treatment on the microstructure. We will now discuss the relationship between the microstructure and mechanical properties in order for us to be able to design the microstructure of material for profound properties. Microstructure that will be discussed: fine and coarse perlite, spheroidite, bainite, and the martensite. Except for the martensite, two phases are present. In the perlite, in the bainite, in the spheroidite, you always have these two phases, the ferrite and the cementite. Except for the martensite, it is a single phase only, does not consist of the same things that you have. The crystal structure is different. It is a BCT crystal structure. Cementite is a very hard structure or compound. Is much harder but more and more brittle than the ferrite phase. So addition of the cementite to the phase there makes the perlite phase harder and stronger as well, but also reduces its ductility. So talking about the perlite, the first phase, increasing the fraction of the cementite in the perlitic structure in the steel alloy while holding the other microstructural elements constants result in harder and stronger material. So as you add the cementite, you will add more hardness, more strength to the material. How do we add cementite to the structure? Well, basically by adding carbon, because at room temperature, the solubility of carbon in the iron as a BCC crystal structure is very low. You see, the solubility of the carbon in the BCC crystal structure is 0.022. And therefore, any extra carbon content in the material goes and forms what? Forms the cementite, basically. It does not go in the ferrite formation. So it forms the cementite phase because of addition of any or availability of any extra microstructure carbon. The yield strength, tensile strength, and hardness increase with increasing the percentage carbon. Percentage carbon, which means also the percentage of the cementite. because all that carbon goes into the development of the cementite basically. While the ductility in terms of percent elongation and percent reduction in area and toughness as well, which relies on the ductility also, decreases in the material because of addition of that brittle, high strength cementite phase basically. The layers of the ferrite and cementite also affect the mechanical properties of the material. We have talked about that. I just talked about that here. The layers, which means that how thick. Now, if we have here the perlitic structure, we have the ferrite and we have the cementite. You see, or am I having it here? You see, I'm not having much more. I will draw another one. So let's say we have the cementite here, and the white color is the ferrite phase. So the thickness of the cementite phase, the boundary in the cementite between the cementite and the ferrite affects the mechanical properties, being coarse or being fine. When we have fine microstructure, we have a lot of the second phase boundaries there, and a lot of much more phase boundary grain boundaries as well. So this is what I have already explained. Having it coarse or having it fine affects the mechanical properties of the material. Same here. The fine perlite is harder and stronger than the coarse perlite, but less ductile. We have already explained that. With fine perlite, a greater phase boundary, not only phase boundary, but also grain boundaries as well. In addition to that, per area of volume exists between the ferrite and the cementite. So this is one reason for why you have. So you have much more grain boundary and phase boundary areas, more resistance to dislocation movement, the material becomes much stronger. Another reason is that, which makes it very strong, because of the, if we look at the cementite here, when it becomes very fine, actually, fine cementite, the cementite is very hard, as you could see in this area now. When you have very hard microstructure surrounding the ferrite phase, it would not allow the ferrite phase to plastically basically deform. Imagine you have two very strong muscle builder guys standing, one here and one here, and you have a small boy in between them. Well, whatever movement that this boy can do, he cannot basically do anything with regard to the boundary. These two very strong persons there. So when the ferrite phases are very thin basically, and the cementite phases are thick enough with high carbon content, this causes this the thin layers of ferrite being unable to basically contribute to the deformation process in the to the deformation behavior of the material. They cannot contribute much, and that's why the material becomes also very strong. Strong rigid cementite phase restricts actually the deformation of the soft ferrite phase and region adjacent to the phase boundary, and the phase boundaries also resist the dislocation movement there. So we have the phase boundary, the second phase boundary, the grain boundaries, and being restricted to move as well. This all causes the perlitic structure to be harder and stronger there. So this is why fine perlitic structure are much harder and stronger and less ductile basically than the coarse perlitic structure. If we want to compare the behavior of the phases there, you could see this is the yield strength, the yield and tensile strength of the material. This is the composition of carbon. Of course, as we increase the carbon content, we are increasing the cementite, which is shown here as well. As we increase the carbon content, we are increasing the cementite phase basically. As you could see, increasing the carbon content or increasing the cementite causes an increase in the yield strength, which is shown by that, an increase in the hardness, in this case the Brinell hardness is used, and an increase in the tensile strength of the material as well. But on the other hand, with increasing the carbon content of the cementite there, reduces the ductility. This is in terms of the percent elongation, and this is in terms of percent reduction in area, and also reduces the toughness of the material. Impact, IZ impact energy is shown here, which you have here. So which gives a rule of thumb basically here that increasing the strength, obviously you can see, and the hardness of the material reduces the ductility and the toughness of the material as shown here. This is just the same, we are showing the same figures here just to distinguish the microstructures that we are having here. Below 0.76 or 0.77 there, we have the hypoeutectoid. Remember that we have the eutectoid microstructure at this point. If you pull in this way, if you pull in this way and pull in this way, this deforms a hypoeutectoid microstructure, which consists of the primary alpha and the perlite phase. This is the eutectoid. This is the eutectoid, and this is the hypereutectoid. So if you are pulling from this in this range, basically you have the cementite basically forming there. So you have the primary cementite forming, and then all the austenite goes into the perlitic structure. So you have primary cementite and the perlitic structure there occurring. So this is why I'm looking at that. This is the eutectoid microstructure. If we are at carbon contents below 0.76, then we are having a hypoeutectoid microstructure, which looks like this. Mostly you have the ferrite phase and the perlitic structure occurring there. In the case of hypereutectoid, we are basically having the cementite there, and then you have the perlite there. So mostly you have the cementite phase in the material, which is very hard, and people are not interested in this very hard microstructure in general. And this is what we are having. Again, we have increase in the hardness, strength, yield strength, and tensile strength, with increasing the carbon content while reducing the ductility and the toughness of the material. This is just to help showing things. Spheroidite, another microstructure. In addition to the perlite, we have the spheroidite. The spheroidite has less strength than and hardness than the perlite. It has much lower strength basically. However, it has high ductility. As you could see here, if we are comparing the fine perlite with the coarse perlite and the spheroidite in terms of the Brinell hardness there, you can see that fine perlite is the hardest one, and then you have the coarse perlite, and much lower than that is the spheroidite. The spheroidite is much less harder and strength as well for the same reason. On the other hand, in terms of ductility, if you compare the three phases there, you can see the spheroidite is much more ductile than the coarse and the fine perlite. Of course, fine perlite will be less ductile than the coarse perlite, but the spheroidite is much more ductile than the fine and the coarse perlitic structure. Why is that? I'm explaining that here. I already explained that before. If you remember the formation of the spheroidite phase, how did that happen? Actually, how does it happen? It happens by cooling, heat treating the material basically, and going in the perlite zone. Or on the other hand, you can do that, avoid the nose as well of the TTT diagram, and go in the bayanite phase. And then after keeping it for a long period of time, the spheroidite transformation will occur. So when you reach here, the spheroidite is going to form. How did we reach into that from, let's say, for example, from the perlitic structure, which has this lamellar configuration, to the spheroidite, which has spheres, circular shapes, basically, which we said here, that this is the spheroidite last time. Spheroidite going from this lamellar configuration of perlite to the spheroidite by reducing, actually, because the grain boundaries and the second phase boundaries are at much higher level of energy. they are much more chemically reactive. So that's why when we keep the material at, you remember the sweating of we said we keep Khalid Ibrahim in the summer, right? I explained that last lecture. So keeping the material also at this large temperature, material tries to lower its total energy. So it selects the parts which has very high energy, and those are the grain boundaries and the second phase boundaries. And it goes to the least interface, to the least second phase boundaries, and the least second phase boundaries is developing what? The spheres, because the sphere has the least, surface area. And making the least surface area here means what now for us here? Making the least surface area, the spherical cementite phase has, in the spheroidite, has less phase boundary. So this means that the phase boundary is least in the material. When the phase boundaries are least in area, it leads to what? It leads to less reinforcement effect and less resistance to dislocation movement. So when we have a large grain boundary and second phase boundary areas in the material, you have much more resistance, as in the case of spheroidite perlite that we have explained at the beginning here. You have much more grain boundary or second phase boundary area here. In the fine you have more than the coarse, so obviously this will be more resistance to dislocation movement. And the same thing with the spheroidite. It has actually the least area. The least area means it becomes the weakest actually. It has the least resistance to dislocation movement and the least strength phase as well. So in terms of hardness, we have the fine perlite first, greater than the coarse perlite, and coarse perlite is greater than the spheroidite. In terms of ductility here, this is the ductility we changed here. We're looking at percent reduction in area. The fine perlite has less ductility than the coarse perlite, and the coarse perlite has less ductility than the spheroidite. Spheroidite is much more ductile than both of them.
Doctor?
Yes.
Time is up.
Yeah, I will take another two or 3 minutes, please. Okay. Bayanite mechanical properties. Only this slide, and we will stop. Bayanite mechanical properties, because the bayonetic structure, we said it's very, very fine, or much finer than the perlitic structures, and obviously than the spheroidite structure. They have very much finer structure there. We have a smaller alpha ferrite and cementite particles or rods there, because we said the bayanite consists of strips basically of the ferrite and needles of the cementite phase, and they are very finely dispersed in the material. This very fine dispersion causes, this fineness of the dispersion that you have here causes more resistance than the perlite, than the case of the lamellar configuration in the perlite, the resistance to dislocation movement, and therefore generally are stronger and harder than the perlitic structure steels. And not only that, actually the bayanite phase is a very interesting phase, that it gives, actually it exhibits a desirable combination of strength and ductility. Not only that, it has higher strength, but it shows also high ductility also compared to the perlitic structure, and this is what you want. I don't want to prolong talking about that, but as you could see from this also, you could see this is in terms of hardness also, the perlitic structures are having higher hardness than the bayonetic structure have higher hardness than the perlitic structures there. And okay, I will stop now. Yes.